Okay, so in this section, we are actually going to calculate the rate of reaction. And what we're going to focus on is how is the concentration changing as a unit of time. So generally speaking, concentration is easy to measure in chemistry. And what you'll find is a lot of grade 12, like when we do equilibrium, we're going to focus more on concentration instead of moles. It's sort of like the next step, okay? So sometimes it is written, rate is written as the change in concentration over the change in time. We usually use little t to mean concentration. We reserve big T for temperature. And even more so than writing out the word concentration, what we're going to use are square brackets. Okay? So if you're talking about, say, the concentration of water, for example, no, that's not a good one. Let's say carbon dioxide, then instead of writing concentration of carbon dioxide, we're going to use this. Square brackets, okay? So again, you're going to see this notation again, actually basically for the rest of the quad, So reaction rate is, we are going to express it as the change in the amount of reactant consumed or produced. So you can do this sort of relationship for either a reactant or a product per unit of time. We usually use seconds, sometimes minutes, but most reactions, we don't want them to take hours, right? So it's usually a smaller unit of time. So again, this section really relates to calculus. You sort of start this kind of thing in functions. So those of you that should continue with pure sciences, you often have to take math as well. Okay, so we're really going to do three kinds of things here. We're going to write expressions of the rate of change in concentration per unit of time. And then we're going to look at what happens if you have actual data. So when you're asked to write an expression, so the reason that here in this example it's capitalized, because all you're given here in this kind of question is the reaction. No actual values for concentration or time or rate, okay? So all we're going to do is write an expression. So you can express the rate as a change in concentration of product, as well as a change in concentration of reactant, and they have to be related. So we use the coefficients all the time. We call that the mole ratio. So for example, in this reaction, every cycle or every time a reaction occurs, it's going to react in the proportion 1 mole of this to 1 mole of this to 2 moles of this, right? That's the recipe, so to speak. And then you can adjust it. Okay, but in my lab, I only have 0.5 of N2. So that would mean you use 0.5 of O2 and only 1 of NO, right? So that's what stoichiometry is, changing the amounts of moles based on your mole ratio. We looked at last unit, changing the amount of energy based on the mole ratio. So now we're going to look at changing the rate based on the mole ratio, okay? So, and you can't create something from nothing. So it has to follow the recipe. And the same sort of thing. If you're trying to make chocolate chip cookies and the recipe calls for flour and you choose not to put in the flour, your cookies are not going to look like you would expect them to look, right? That reaction is not going to work. The same thing here. So, and you can do plenty of things with this, like limiting reagent. So one of the reactants, if it was going to limit how much of the reaction can occur. Last unit we saw the questions often said excess to try to, don't worry about the other reactant. There's more than enough of it. So that kind of thinking. So now we're going to look at which reactant is going to affect how fast a reaction can occur. So that's really 6.1. We're going to look at calculating it, and then we're going to look at a rate law, it's called, in 6.3. Okay? So again, looking at how a reactant can change or affect how fast a reaction can occur. And again, if you think about it in a practical way, let's say you're running the Maria chemical factory. If one of the reactants, you need a lot of it in order for a reaction to occur, she would have to account for that. If you're trying to make the reaction faster and one of the reactants will have a greater influence than another reactant, then you'd want to put more of that one in. So all of those kinds of things have to be taken into consideration. And we're going to look at how mathematically you can do that. Everybody loves quantitative, right? So one of the things about writing an expression is if it's going to be increasing or decreasing. And sometimes students it's like you can do all the difficult stuff, but then if something is meant to be sort of common sense, it's like you block it out. Okay, so try not to do that here. So it's really 50-50. It's either increasing or decreasing, or a positive rate of change or negative rate of change. So logically, you would know, again, don't push out of your brain things you already know. If you're doing a reaction, is the product going to increase over time? Of course it is. A reaction makes products, right? So it's going to have a positive rate of change. And then if you have a reactant, that concentration is going to decrease. So you're going to get a negative rate of change. The one little caveat to that is this. So this says reaction rate is always positive. And what they're trying to imply here is like a numerical value. So if you have a numerical value like 5 moles per liter second, how is concentration changing over time? Then if it's a reactant or the rate of decrease, when you do the math, you would get -5. But you can't write that down. And the reason is when you have time, if you have a negative, then it's ambiguous. Do you mean negative time, like you're going backwards in time? No. Now you might say, we're obviously talking about the concentrations decreasing over time. However, we can't have ambiguity in our numbers. So usually what students will do is write 5 moles per liter second. They won't make the number negative, and they just write the word rate of decrease. So when we do our examples, I'm going to do the math and have a negative number based on just the math. But because our numbers actually mean something, I'm going to write my final answer as a statement, okay? So that's one thing we're going to do. Here, we have no numerical values for rate. All we're given is the equation, and we're asked to write an expression. So it says write an expression for the rate of production of products and the rate of consumption of reactants. It doesn't matter which one you choose. It's essentially the same thing because we're going to follow this stoichiometric ratio here, 1 to 1 to 2. But I'm going to show you both, and you can pick whatever you like, okay? All right, so it says, A says the rate of production of products. So I'm going to start, that means I'm going to start with the products, okay? So when we do rate, it's the change in concentration over time. So if you forget and you want to remind yourself, concentration is moles per liter, and time, like I said, usually seconds or S or minutes. We don't usually use hours, hopefully. So we're going to write it as a rate of change because that's all we can do. So it says the rate of change, it says expression, versus a question like we're going to do in a minute where you're actually given a number for rate, okay? We have no numbers here, so decide for yourself how that's going to stand out to you, okay? So the rate of change is always going to be change in something over time, no matter what. So like in math, you'll do the change in speed over time, distance, whatever. You can do a whole bunch of rates of change, okay? I feel like there's an entire unit on it, isn't there? Yes. So that's what we're going to do here. So I'm going to draw a skeleton first. And again, in part A, it starts with products. Why did I start with the product? Because that's what the question says. Okay? We're going to do both. So change in the concentration of NO. Why NO? It's the product. Again, because of stoichiometry or the law of conservation of mass, you can't create something from nothing, okay? So the rates of change have to be equivalent based on the mole ratio. So we'll add the coefficients in a minute. First, we're just gonna do the skeleton, okay? So we have change in concentration. Now I'm gonna do, so I started with that because that's what it said. Again, when you go to do these questions, I don't care which way you do it. But I'm gonna show you both. So change in concentration of product. And now we need the two reactants. I'm just gonna go in order that they are listed here, okay? So if they were all the same, if they had the same coefficients, if they were all reactants or all products, we could leave it like this. It's all equivalent. However, that is not true. So we need to add two things. We need to add the coefficients, and we need to state whether it is a product and has a positive rate of change or a reactant and has a negative rate of change, okay? So actually I'm gonna make this a different color. So the product has a positive rate of change. So when you do this, you want to show that the rate of change is positive, not the top of the fraction or not the bottom of the fraction. When it's positive, it doesn't really matter. The problem is going to be over here when we have time in the bottom. Again, we're trying to decrease the ambiguity. Is it negative? Like, are you trying to say go backwards in time? No, we are not, okay? So you can do two things. You can either write the positive sign in the middle outside of the rate of change. Some people stress about that and they're like, is mine in the middle enough? What you can do then is put brackets. So what you're saying is this whole rate of change is positive. Okay, why is it positive? Because it's a reactant. I mean a product. And that's logical, right? You would know that. Oh yes, products get produced. Okay, that's logical. So then when you have the two reactants, over time, reactants get used up. Their rate of change should decrease or be negative. So again, decide for yourself if you think you can make it negative right in the middle. Okay, if you're like, I can't do it, I don't know if it's in the middle enough, put some brackets. Okay, you're saying this is a reactant. Over time, its rate of change is going to decrease. So if you are a color person, I put the same color here and the same color here, okay? You don't need to do that, but. Okay, but we're still not done, right? So now we have our skeleton, we have labeled the reactants, we have labeled the products. So without even having this equation, somebody could look at this and say, oh, this must be what's being produced because it's got a positive rate of change. It's increasing its concentration over time. These two are reactants because they're getting used up over time, okay? So now we need to add in the coefficient. And what students often want to do is this, because the 2 is on the NO, but you can't do that here, okay? So you kind of have to think about what's happening. So every time a cycle of the reaction occurs, I'm going to use circles and triangles and squares, okay? So let's say we have cycle 1. One of these reacts with one of these. How did I know it's 1? Or what did I use to base that on? Yes, the coefficient, okay? And then how many of these would be produced? 2. I let the reaction go again. So 2, or 1, 1, 2. So over time, is this being produced faster than these two are being consumed? Each one separately? Look at one at a time. Yes, right? You're getting twice the amount. And that's what we're trying to do. How is it changing over time? So down here, this is saying the NO is being produced faster or slower than this is being consumed. I think I heard someone say it. Is this being produced faster than these two? Yes. So in order to make faster, does that mean a bigger rate? Yes. So how do we make a bigger rate? The 2 actually goes here. And it happens, these are both the same. So a very ruthless kind of question would be that every single one of them has a different coefficient, which we're going to actually, the next example is a little bit like that, okay? So now, again, say it in your head. The rate of consumption, or the rate of production of this product is twice as fast as N2 is being consumed and twice as fast as O2 is being consumed. So then B, let's do the other way. Write your skeleton, but this time we're going to start with reactants. Reactants are still consumed. Products are still produced. I'm going to leave the brackets out this time just for clarity, okay, so it doesn't get so crowded. I don't really know why, to be honest. Lots of times this way actually makes more sense to students. I don't know what it is. So if you like this, do this. If you like this, do this. I don't care. Start with the reactants if you want. Maybe it's because that's the way you're used to thinking of a reaction. It doesn't matter. Okay, so now we're saying, is the rate of consumption of N2 the same as O2? Are these the same? Do they have the same coefficients? Yes, so they are the same. And then it doesn't really matter. You can sort of ignore this one for a second and just focus on these two because these are now the same. It doesn't matter. So the rate of the consumption of the reactants, is it faster or slower than the rate of production of product? Pardon? Slower. How much slower? Half. Or you can think of it like these two are being consumed half as fast as this is being produced. Okay? Or this is being produced twice as fast as these are being consumed. These are equivalent. It doesn't matter. The negative rate of change goes with the reactants, positive with the products, and then you just have to put the coefficients in the appropriate spots. It is tempting to just put the coefficient with the substance, but you're trying to relate the other substances to that one. So it's kind of opposite if you like a shortcut. So the rate of production of this is twice as fast as these are consumed because 2 is 2 times bigger than 1. The rate of consumption of these two is half as fast as NO is produced because 1 is half of 2. Yes? It doesn't matter. Bless you. So you could do, let's say, which we're going to do in a second, let's say you were given a real number. You could put it in here and then multiply by half. You could do the concentration times 1 divided by the time times 2. You got the same answer. Yes? Okay, let's do another one. That has a few more coefficients, but that's okay. So we're actually going to do the expression, and then we're going to do stoic. So you have a choice when you do B and C. If you want to continue to use the ratio like we did before, that's fine. Or you can use the expression you write. Now, most of the time students hate writing the expression, so then they don't want to use it later. They would rather do a ratio, but it's up to you, okay? So it does say write the rate expression in terms of N2O5. So again, I've told you which one to do. When you're doing this, I don't care which one you pick, but I'll just pick N2O5. So I'm going to start with N2O5. It's a reactant, so its rate of change is going to decrease. Let's say you were given this question. Most students would actually pick oxygen to start with because it has a coefficient of 1, and then it's sort of easier to relate the other ones to it. That's a trick you can use if you want, but it doesn't really matter. Okay, so this one says N2O5. So now I'm going to look at how does N2O5 relate to NO2. So 2 and 4 and 1 are easy numbers to sort of pick the multiples of. Again, you could use like 2s and 3s and 5s, which is like the nastiest of nasty, okay? So generally speaking, that's not what we're going to do here. So N2O5 has a coefficient of 2, and then NO2 has a coefficient of 4. So 4 is 2 times 2, yes? So that means that NO2 is being produced faster than N2O5. Again, there's a bunch of ways to do this. Whatever you put on the left, I recommend you leave this as a 1 and then sort of think how this relates to this. So the rate of N2O5, which is 2, how is that related to NO2? Is it half? Is it twice? Yes. It is half, yes. Okay, so then once you're done, say it again. The rate of consumption of N2O5 is half the rate of production of NO2. Okay? And then this one now is going to be, yes. So the rate of consumption of N2O5 is twice as fast as O2 is produced. Okay, so then B and C actually want you to calculate the rate. So again, you can plug the number in to the expression you've written, but again, it's like students hate that, and they're like, no, I don't want to do that. So we can do a ratio like we did in the last unit. So now we're going to use this number. Versus writing an expression. Okay, now we're actually going to calculate the rate. To be honest, this section loves scientific notation. So if you don't know how to do scientific notation on your calculator, let me know and I'll come help you. Or you just have to religiously use brackets everywhere, okay? So if you don't know how to do EXP, sometimes it's a little EE, sometimes it'll say on your calculator to do scientific notation. For whatever reason, the textbook often will give you the homework, like the values in the homework as scientific notation, okay? I don't care what your answer's in, to be honest, but it definitely is in there in the textbook. So we are looking for the rate of disappearance of N2O5. So I'm going to call that X. So instead of kilojoules, we're going to use rate, this unit. What goes in the bottom? If we're doing N2O5, what do you think goes in the bottom? Yeah. I'm going to call it mole. You can put coefficient. We are given this for NO2. Yes, Simon? Yes. And its coefficient is 4? So when you do Stoich in this unit, the rate itself is often nasty, but the coefficients are usually straightforward. So, there's positives and negatives. Because I am squished, you're going to do this, divided by 4, and times 2. You can also do cross multiplying. 2 times 5 times 10 to the negative 6 divided by 4. Again, you can, if you're going to type this in, you have to do bracket 5 times 10 to the power of negative 6 in brackets, then do the multiplying and dividing, and you should get 2.5 times 10 to the negative 6. whatever they give you for units, so if it's moles per liter second, moles per liter minute, whatever, just use that. Make sure you have units. Most of the time it is going to be seconds, not minutes, but just in case. And then we can do the same thing here. Now you can use your answer for this. Or again, for whatever reason, people don't trust themselves. Usually people go all the way back to the original, which is fine. What's the rate for oxygen? Its coefficient is 1. Or some people like this way too, because then this side of the ratio is the same in both questions. But again, really nice coefficients. Basically, you're just dividing by 4. Do like here. Yes, Simon. Okay. 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 So the second type of math we have to do is average and instantaneous rate. So functions is not a prerequisite for this class. We're going to do exponential curves, which we don't have the equation of the line for. So when you have actual data, we're going to simply find slope, okay? So in math, you may, like slope we talked to as about like rise over run, change in y over change in x. It's going to probably be easiest for you in this unit to think of it at like y2 minus y1 over x2 minus x1. So in our case, always, 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 time is going to be on the x. So you're looking for time 2 minus time 1. And always, always, always on the y will be concentration. I'm going to use the square brackets. I'm going to use the short form, okay? Because I don't want to squish. So the change in concentration over the change in time is reaction rate. So slope is going to be rate. So yes, in math, when you do slope, sometimes it's just random x and y values. Ours are not going to be random. It'll be time, concentration, which has units. So please make sure both of these, you're going to need to have units. And again, usually we use seconds, okay? So moles per liter, concentration, time is seconds. Yes? And I'll show you how that works. So there are essentially two kinds of reaction rates we're going to look at, average and instantaneous. So when you have an average, the difference is you're given a time interval. So between 1 and 3 seconds, we're going to do 1 and 11 seconds. 0 is often an interval, 0 and 15 seconds. So one of the questions in the homework wants you to calculate the rate, and they give you a bunch of data. So basically all you're doing is concentration 2 minus concentration 1. Time 2 minus time 1, and you divide. Okay, so you're basically doing like grade 9 math, okay? That's really what you're doing. In the end, people stress a lot about what's x2, what's x1. It doesn't matter, especially now, because when you have a numerical value answer for reaction rate, are you going to leave it as a negative? No. No, never, no, okay? Because we can't say for sure, once you do the dividing, oh, are you going backwards in time? And again, you're probably like, Ms. Todd, we're obviously not going backwards in time. However, we want to make sure that, some rinky-dink scientist who's reading our data doesn't think, oh, does that person think that they're going backwards in time? But whatever. So the way that we standardize it, it's always about the standard. We are not going to leave the numerical value for slope or for rate as negative, okay? So if you are not familiar with this, when you do average, we're going to do the slope of a line, which is called a secant. And the big thing about a secant is that it's 2 points on the curve. So usually you're given a time. So you'd be given time 1, and time number 2, which is a later time, and then you connect the dots. Really, when you do secant, you actually don't even really need to draw the line. It doesn't really matter. But unlike instantaneous, so instantaneous will be 1 point, right? Instant. Average is going to be 2 points on the curve. Usually the 2 points that you're given are time. So the average reaction rate is going to give us an overall idea of how the reaction is progressing. However, obviously it does not tell you what the rate is at a specific time. So find the average rate of reaction from 1 to 11 seconds. So what I would do is just, even if you can't really see the grid, let's just go up by ones, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think the secant that the textbook picks sucks. So let's draw a new one. Okay, we're going to do 11 seconds and 1 second. I'm going to do my very best on this board to draw a nice line. But like I said, when you do average, you really don't even need the line because your points are going to be dictated by the times that they give you. So where slope is rate, so you can think of it like the rate equation or the slope equation, it doesn't matter. When you do average, it's a little bit easier because the bottom will be dictated for you. We want to go from 11 seconds to 1 second. Okay? And then, yes, we are going to have to estimate. And it's okay. We're going to do a good job. Again, let's just go up by ones. Simon. Just kidding. So maybe let's call this 0.8, 0.9. What do you guys like? 0.8? I like 0.8. $4.1. Okay, so now, yes, this change in concentration is going to be negative. We're going to divide by 10. So now we've got moles per liter divided by seconds. So usually we write that as moles per liter seconds. You might see it like moles per liter divided by liters divided by seconds. To be honest, some scientists will write it like that, but we're going to, usually your textbook uses this notation, okay? Can I leave my answer like that? No. So you can simply rewrite the answer. Or a sentence. Therefore, the rate of decrease So this is a little bit trickier to do graphically because you have to draw what we call a tangent. So a tangent line is similar to a secant line. However, it only touches the curve at one point and it does not cross the curve. So you do not draw a tangent like this. Okay, that's not a tangent. So this picture has two examples of tangents, and the way that you can tell this question, usually it says calculate the instantaneous rate, or it'll say calculate the rate at 3 seconds, 5 seconds, whatever. So you're not given an interval this time. It's not between this and this. It is just one time. Again, the questions, you'll be given the time, and then you have to figure out how you're going to do the slope part, or the change in concentration and the change in time. So we have the instantaneous rate of reaction at 3 seconds. So again, let's just label these 1, 2, 3, 4, 5, 6, 7, 8. I know in functions there is a way you can make a chart with increments increasingly closer to the value that you're looking for, but we don't have the equation of the line, and we're going to not make it that complicated. We're just going to keep it simple, okay? So it does say 3 seconds. So find where 3 seconds. That's the rate that we're looking for. And then try to draw the best tangent you can. So you don't have to do, you don't want it to cross. You just want it to be equally above and below the line at that 3 seconds. So like this one is borderline to me, like it's okay. Pretty good. So when you, let's say you had to do instantaneous rate, usually I accept a wider variety of answers because we're going to estimate more versus average, which is a little bit, definitely the time section or the time values on the average rate are easy to find. So when we're still going to do slope because slope is rate. And so when you do slope, this is like old school grade 9 math, maybe even grade 8, where you had to find slope using, and you have to estimate the points, which is everyone's least favorite thing to do. So what I recommend that you do, you pick the nicest points you possibly can, okay? So when I look at this tangent line, I like this, and I like this. Because that's 4 seconds and 2 seconds. So at least the bottom, I'm pretty sure is going to be okay. So again, decide how you like to write it, y2 minus y1 over x2 minus x1, or in the rate form, same thing, okay? So like I said, when I pick those 2 points that are on my tangent, so it crosses exactly at 4 and 2, and then we just have to estimate the top, okay? So this is about, let's call that 1.9. This one, I'm going to call that 2.95. So yes, we are estimating, but we made good estimates. So again, this is obviously decreasing over time. We're going to get a negative number in the top. But again, when you get your final answer for rate, you are not going to leave it negative, okay? That is bad form in science. Okay, so negative 0.525. And so again, decide, I'll write it in a different color, just like I did last time. Either leave your final answer as non-negative or write a statement. So these are both reactants. These graphs are both representing a reactant. It just says concentration of reactant. It doesn't say what it is because they're decreasing over time. So slope, when you're given an interval, that's average rate or slope of the secant. And when you're given one particular time, then you draw the tangent and find the slope of that. You would do the same thing if it was a product, except, I'm just going to sneak it in up here. It's still time and concentration. However, the graph is going to be increasing, right? So you would find the slopes of tangents or secants. The shape would just be different, okay? So this would be a product. But the same principle. It'll always be time on the x, concentration on the y. How does the concentration change over time? Does it go down? Is it a reactant? Or does it go up? Or is it a product?